Hello all, welcome to this lecture. So in this lecture we are going to have couple of simulation exercises. So these are based on whatever lectures we have covered so far for the vector control of the PMSM drive and vector control of induction motor drive. So we are essentially having couple of examples on that, and then we will see how these different quantities controllers are responding to the given input. So what we have here, first exercise is basically kind of high speed PM drive. The parameters of the motor are mentioned over here. So this motor is basically rated up to 50 kilowatt and rated torque is somewhere around 96 Newton meter. The line to line voltage for the machine at rated RPM is somewhere around 325 volts. The rated speed can go up to 5500 RPM, and the rated fundamental frequency given for the motor is nearly 1 kilohertz, so 916 hertz to be more accurate. And this is somewhere 20 pole machine, and that is how this is done. And for this particular system, what we are considering is that we are taking converter DC link of around 500 volts, and because we are going to operate the system with IGBT semiconductor devices, so we cannot have a very high switching frequency given by that, because the losses and other things also are required to be contained. So we have taken a switching frequency of 8 kilohertz over here, which is corresponding to the fundamental frequency, corresponding to the highest fundamental frequency is nearly 8 times. So this is a special scenario where we are having high speed PM involved, and typically these kind of drives are seen on, say, Formula 1 racing cars or on electric aircrafts, or in fact some of the versions of high-end drones we can see these kind of drives. And what is expected that basically when we are designing a drive which is going to have fundamental frequency going up to nearly 1 kilohertz, we need to have a very strict thermal design for the power converter as well. So we are going to have a compact lightweight power converter, because many a times these high speed vehicles have such demand, and then we cannot have the switching frequency going very higher. So we'll see the structure of the simulation first. So this is where we have considered a 2-level 3-phase inverter, and the motor is connected over here. So motor model from MATLAB Simulink is taken over here, and the parameters are filled in this section. So we are basically loading the same data in the workspace and then using the same for operating this model. So we have rotor flux oriented vector control to be implemented. So for that we need to have measurements of the line current, we need to have certain feedback taken from the speed encoder, position encoder over here. So we are taking omega and then the position of the rotor as well. So these are the feedbacks generally expected to be available on the system, and this is taken, and then these values are basically transformed to DQ, frame of reference, as and when needed. So this is how the whole control structure is going to look like when we are implementing for the vector control. We have speed reference provided over here, which is basically given in a manner that the motor is able to operate on all the 4 quadrants of the torque speed plane. So we have speed going from 0 to maximum value, then coming down to minimum value, and then going on the negative direction with the highest value, and then coming back to the 0 value. So this is how the speed is going to, the reference is going to be given, and the speed is going to track that. Now for doing it, PI controller implemented over here, the speed PI controller is basically going to generate the reference for the Q axis current. So we have the Q axis current reference generated over here, which is basically fed to the control block for the Q axis current. We have the feedback for Q axis current, and once again the PI controller given over here, which is generating the reference for the Q axis voltage along with no, after addition of the no feed forward terms for the PMSM model. So what we have essentially here is that each block is having saturation limit given for the output unit, and also the saturation limit is linked to the integrator. So whenever the output quantity is reaching up to the saturation value, the integration process is being stopped over here. So this is done for the Q axis current controller as well. For the D axis current control, because we are doing kind of maximum torque per ampere control for the PMSM, we are giving zero current reference on the D axis for the D axis current, and the controller will generate the reference for the D axis voltage after addition of the feed forward term on the VD side. So we have this VD and VQ reference voltages given over here, which are effectively then converted to MR, MY, MB, the three-phase modulating signals with the suitable unit vectors taken over here, and these modulating signals are compared with the triangular carrier having a constant switching frequency of 8 kilohertz as stated earlier. So after the comparison, we are generating the gating pulses for the top and bottom devices, which are essentially fed to the devices shown over here, and then we have the appropriate measurements and plots given over here. So if we try to see how the reference speed and then the required torque are being tracked, so we have the response given in this manner. So as said, we are providing a reference, and then the actual speed is also plotted on the same graphs. So we can see that the yellow reference is being tracked by the actual speed, which is shown in blue, and this is very accurately tracked, so which is why these two are looking quite indistinguishable, and the speed is basically settling down at certain speeds. So we are having different levels of reference given at different intervals, and the torque is set according to attractive load traction load, where we are having the highest value of torque given in the initial stage of the speed, and as the speed is progressing, the torque value is coming down. So the speed has completed the ramping up process, and now it is ramping down to say nearly zero value, and then it will be proceeding for the rest of the negative cycle. So in response to the speed reference given by the blue waveform, the yellow waveform is able to track with some minimum ripple on that. However, corresponding to the load torque provided over here and the acceleration required, the controller generates reference for the Q axis current, and that is basically plotted over here. So we can see that this yellow waveform is the reference generated by the current controller, the speed controller, and then the blue waveform is the actual ISQ, which is generated by the system. So as we can see over here, these two are overlapping, which means the demand given by the current controller is given by the reference is basically fulfilled by the current controller, and it is tracking quite quickly. In the initial phase also, it generates a command which eventually saturates. So we have the saturation limit as suggested earlier according to the rated value of the rated value of current for the motor drive, and this is where it is generating the highest possible torque, and it is able to accelerate and overcome the load torque. On the other hand, if we see the d-axis current, so because there is zero reference given, so it is essentially maintaining the average value 0, although there is ripple coming on the actual current which might be on the higher end due to low pulse number operation, but the average value maintained by the current is at 0 value. The three-phase modulating signal can also be seen over here. So we can see that as the speed is increasing, the modulating signal is also rising in magnitude, and we have some switching ripple components reflected on the modulating signals as well. And this has reached the highest value when our speed is at the maximum value, and then as the speed reference is going down, it has basically come down to a lower value. Now once we are witnessing the speed reversal at this junction, we can find that the sequence RYB is basically getting changed to RBY, and this is how it is able to go for the negative direction of rotation. So same impact or same effect is seen on the current as well. So we have the three-phase current for the permanent magnet machine. So it is having very high value in the beginning because of the high torque demand, and as the torque demand is going down, the value of the current is also reducing, and for the speed reversal part we can see that the current sequence is being changed from RYB to RBY. So this is the response generated by the motor drive controller, and this has gone and saturated to the second level on the negative side. Once again, the next reference for the speed is generated, and it should be seen that the reference for the speed is essentially a ramp reference. It's not a step reference given. Once again, the ISQ is also seen to follow that. So as and when the braking requirement is there, it is able to return back to a lower value to facilitate that along with the load. And this has saturated to nearly the highest speed limit on the negative side. So 1500, 5500 is the RPM is the rated speed, and this is settling to 5500 RPM on the negative side. So we can see that the response of the speed controller is quite fast, and it is able to track the desired speed. With the given DC length and the saturation limits, we are finding that modulating signals are well within the unity value. So there is no over modulation observed in this case. However, there are some distortions near the highest speed range. So that is on account of reduced pulse number. The interesting fact can be seen on the torque that though we are having the lower value of torque demand near the highest speed, we are finding that peak-to-peak torque ripple is quite high, and that is once again on account of the current ripple being present over there, which is at the highest value. So here we are witnessing peak-to-peak torque ripple of around 50 Newton meter. So the PWM technique must ensure that these torque pulsations or torque ripple are not hampering the life and the performance of the motor drive. So these are the key quantities that can be observed in this simulation. and we are able to operate the permanent magnet synchronous machine on either side of the speed directions with the desired load torque, and we are finding that dynamically the controllers are responding very well to the desired to the reference value. So hence we can say that the implementation of rotor flux oriented vector control and the design of controllers is very much effective over here in finding this output, in getting this output. Now next I would like to move to the simulation which is related to rotor flux oriented vector control for induction motor. Again pause कर दो because I need to stop and then start again. कितने मिनट्स हुए? 20 हुआ?
नहीं सर, 17
So in the next example, we are going to have vector control of induction motor drive, and here we have considered one of the motors which are being used for the traction application, railway traction application. So this is 850 kilowatt. The motor which we have seen in the previous lecture, FRA 6068 motor. The parameters are also mentioned over here. So this motor is having rated torque of nearly 6000 Newton meter, and the rated line to line voltage is around 2.2 kilovolt. Fundamental frequency is 65 hertz, and the rated speed under the rated torque conditions is basically 1283 rpm. So the parameters are basically mentioned over here for the rotor and stator resistance, the stator and rotor leakage, and then the magnetizing inductance. Inertia is taken as 5 kg meter square. Usually we have bulky system operated from these high power motors, so which is why inertia is taken as 5 kg meter square. Number of poles for this machine are 6, and we are considering a DC link voltage of 3600 volt. So basically we are trying to match 2.2 kilovolt with while operating the converter with sine triangle PWM. So we are not going for any special PWM technique, any optimal or any other kind of PWM technique. So we are keeping 3600 volts so that the motor operates almost within the linear modulation range of the sine triangle PWM. And switching frequency for this particular application is kept at 500 hertz, and here we are keeping constant FSW, so we are having asynchronous sine triangle PWM. To keep the simulation and to keep the understanding simpler, we have taken in this manner. Now this is the inverter which we are considering over here, 2-level 3-phase inverter, which is basically connected to one of the models given by the MATLAB Simulink over here, and we are having the feedback for the current and speed taken over here. So this is kind of, we are trying to implement the indirect vector control, and we do have the controllers designed for the appropriate action. So we have the measured quantities RY, IR, IY, IB, which is being transformed to alpha beta, and then by using the appropriate unit vector it is converted to ISD ISQ, which is eventually used for the feedback purpose. We are also having the model for the IMR computation, and ISD is taken as the input for that, and IMR, the rotor flux magnetizing current, is basically generated over here, is computed over here. Now we are computing the slip speed by using the ISQ current, IMR current, and the rotor time constant, and this slip speed is basically added to the measured mechanical speed over here to generate the synchronous speed for the machine, and which is basically used for generating the angle for the rotor flux. Now we have different controllers shown over here. So first controller we have is a speed controller, where the reference for speed is provided, and we are basically having the feedback of the speed with a first order filter. The filter cutoff frequency is kept somewhere around, say, 2 hertz, and then we have the difference of the two quantities, the reference and the actual speed, fed to the controller, speed controller, shown over here. However, the value is kept 0 for some time, which is basically an interval considered for allowing the IMR to settle to its final value. And then the error is fed to the controller to generate the ISQ reference after adding the appropriate feed-forward terms. So in case of speed, we do not have any feed-forward term over here. Now, if we go for the ISQ controller, the ISQ reference generated over here is basically then compared with the feedback ISQ, and once again we are giving a time delay before this error is fed to the controller. This is once again to allow the IMR to settle down, and then we have the reference for the Q axis voltage generated after the appropriate feed forward component additions. The IMR reference computed for the machine is basically given as a constant over here. The value is somewhere around 170, and we have the IMR actual IMR computed from the ISD, which is basically fed to this, and a time delay is taken, which is a small time delay, say somewhere around the value of 0.5 second, and then we are feeding it to the controller, the flux controller, which is generating the reference for D-axis current. Now this D-axis current reference and ISD are basically compared over here and then fed to the controller, which is eventually generating the reference for the D-axis voltage after the addition of the appropriate cross coupling or feed forward terms. Now we have the saturation limits given for each and every quantity, and also for the integrator units which are involved in the whole process. So if we see the response of the different sensors over here, so let us first try to see the speed reference and the speed plotted on this second waveform over here, the second middle section of this scope. So we have the orange waveform which is given as the reference, and the blue one is basically the actual speed which is tracking the reference. So we are finding that there are several intermediate steps provided for the speed reference to visualize how the controller is responding, and we are finding that with certain minimal overshoot, the speed is basically able to settle down to the actual reference value. There is load torque which is provided at, say, a certain value, say at certain time, say 7 seconds, and that is where we can see that there is sudden sharp jump in the current also coming over there. The delay of this initial 6 seconds, so the speed reference is started at 6 seconds. Before that, we are ensuring that our IMR is settled. So going back to the controllers, if we visualize the IMR, the reference for IMR is given from the beginning. However, controllers are started at nearly 0.5 second as stated earlier. So once this controller is activated, then the value is settling down to the set IMR reference value, and for that this is maintained at the same value for the whole range of the operation. Now in response to this IMR controller, the ISD reference is generated, and ISD current is basically following the reference, and it is maintaining the value required for the ISD. It is maintaining the value of the ISD current as demanded by the IMR controller. So we can find another observation we can have is that the ripple on the current is continuously increasing. This is on account of the constant switching frequency operation, and as we are going for the full fundamental frequency, we are finding that the pulse number has come below 9. So which is why we are finding that the ripple on the current has become very high. Now if we look for the speed controller as shown in the previous plot, we are finding that the actual speed is able to track the reference with nominal value of overshoot over there, and the second order response that is expected is visible over here. Now in response to this, the error in the speed reference and the actual speed, the ISQ reference is generated, and this is where the ISQ controller is basically responding and generating a reference value which is being tracked by the actual ISQ current. The major change in ISQ reference is coming on account of the load torque applied on the system. So as we have applied the load torque at 7 seconds, we can see a sharp rise in the reference for the ISQ, which is basically countering the load torque and then generating the necessary acceleration required. And then the ISQ value is basically tracking that with the amount of current ripple that is visible on the graph. Now if we see the three-phase current for the motor, we find that in the initial phase of the speed, the ripple is relatively not very high, and as we are progressing for the higher speeds, we can find that the ripple has become very high for the for the given system. So this is once again happening on account of partially the pulse number going below 9, and then secondly, because of this ripple appearing on the current, our modulating signal is also slightly moving towards the over modulation. So if we observe the three-phase modulating signals along with the triangular carrier, we can find that for this portion, for the higher range of the speed, the modulation index has crossed the linear modulation range, and that is one of the reasons why we are finding more low frequency component, low harmonic frequency component coming on the current. Now if we see the modulating signal, three-phase modulating signal, we find that the three-phase modulating signal is behaving very well, and there are some distortions coming on account of the control action and all. However, as and when it is crossing the linear modulation range boundary, then the distortions on the current and the modulating signal are appearing to be more. So in this whole process, we have several more quantities measured over here. So we can see the mechanical speed, slip speed, the synchronous speed, and the theta plotted over here. So we can find that slip speed is more or less fixed as we are applying the constant value of torque. The mechanical speed and synchronous speed are rising continuously with the reference. The angle rho is also changing accordingly as we are going for the higher speeds. We have the current on the alpha beta axis and the DQ frame of reference currents as well shown over here. So we can find that the waveforms are consisting of some ripple, nominal value of ripple in the initial stage of the speed, and as we are moving towards the full fundamental frequency, the ripple on the current is rising, and the peak to peak ripple can be seen to be as high as nearly 400 ampere. So these are some of the things which we need to take care while designing the pulse width modulation technique. And many a times, because for high power motor drives, we do not have many options available for reducing the current ripple. So this is where we need to go for either special PWM techniques, or we need to go for some other topology for the power converter. However, we have seen in some of the complex structures, having more number of devices, more number of power converters in the system can only complicate the electronics design and other systems coming over there. We also have the D and Q axis voltages shown over here. So we can see that VSD is nearly zero or going on the negative side. However, VSQ is having the major contribution on the voltage, and it is rising and reaching almost up to a value of 1.75. We have once again the value of IMR shown over here along with the reference, so IMR is able to maintain the constant value up to the rated speed. There are some small deviations coming on the actual IMR. However, this is found to be within the desired limits. So this is found to be within plus minus 2 ampere. So this is how the system is operated, and the design parameters whatever we have considered during the controller design for the vector controlled induction motor drive are considered, and the different parameters are mentioned over here which are used for the simulation. So the process of validating the design can be followed by having a good realistic simulation, and we can have the controllers and other blocks implemented by using simpler blocks that will give us the understanding of whether the design for the controllers are suitable or good or not. So we can have the validation of different understanding and different designs over here in this manner. And this concludes basically the section that was started along with the vector control and modeling and other aspects. And we have seen all different aspects of the vector control. So we have started with the modeling of the generalized cylindrical rotor machine. From there we have moved to modeling of PMSM, vector control of PMSM, and this was further extended to modeling of squirrel cage IM and vector control of squirrel cage IM. So both these controls are basically done in rotor flux oriented frame of reference. So with this chapter is concluded, and we'll be moving with some different type of motor drives in the coming up lectures. Thank you.